This time I remembered to press the go live button. I didn't do that last time. I was talking to myself for like a half an hour. Okay, hi, welcome to the Sometimes Sunday Math Show. This is a sort of side hobby of mine to understand math, I guess, a little bit, because I think that how to speak machine is really important today, but that's not easy to speak machine if you never liked math. And if you are a math lover already, you may not want to watch this because it may be like, no, don't do it that way. Don't do it that way. So I don't recommend this for real math people. It's more for people who want to engage in math as a hobby. So with that disclaimer, this is the Sometimes on the Math Show. It is the episode 2. Episode 1 was all about 8th grade math in 15 minutes. And that does not do it. I know that. So I'm going to do sort of 2 pieces in the math. 2 pieces here. So let me sort of again check I have a new camera set up, so that's pretty good. Okay, I like that. And okay, so let me see here if I can too many cables here. I'm sort of like in a big room, but how to run all my tech. So anyways, let me see what we have here in my box here. First, I have my colored pencils, very important. I forgot where I got these in Japan a long time ago. They probably they were important purchase. I have my calculator, something my mom Yumi got me when I was a kid. I think she put all of her savings into it, so it's very precious to me. It doesn't work anymore, but I remember it was an important thing for me because I grew up in a poor part of Seattle and was bused across Seattle. And I was bused to the nice part of Seattle, and the kids had all kind of good stuff. So my mom wanted to make sure that I, could represent. So she would just do everything she could to make sure that I could look okay. And thanks, Mom. And so this is my calculator, which was quite fancy to have, and it helped me kind of maybe not get beaten up as much. maybe that's the thing. When you're a nerd, it's not that easy, So anyways. Hashtag, real stuff. Okay, and I have my stuff in here. I've got my self-renewal book, very important. Those of you who are having challenges in your life or career, just read this book and things will be okay. It has a kind of magical power to it. And I've got a pen in here too. Got my pens. All right, pens, so we'll do that. And then let's put this over here. Note to self, make more room for things around me. I hate to put them on the floor. Okay, here we go. All right. So, okay, here we are. We're collected. I forgot another thing I have. I have some money. I'm not going to give it to you, sorry, but I have some coins that I want to use as well. Coins. Got some coins. Okay, good. And I think we can get started. So where were we? In episode 1, we were going over the common standards for math curricula, and we were making it very clear that we're a big believer in teachers over curriculum because teachers make things work. I can't tell you how important I think teachers are because they kind of are considered the kind of accessory to the materials, but like I said, I didn't grow up with a lot, and if it wasn't for a couple of my teachers, I probably wouldn't have made it out of Chinatown in Seattle. So, anyways, teachers are pretty important. So, if you're a teacher out there, thank you, and if you have a teacher out there, make sure you thank them. Okay. So, I have some ideas for how to do this. As you can tell, I'm making notes to myself how to do this better because this is different from what I normally do. But I went over math grade 8, and I stepped over everything too quickly. I talked about how math, let's see here. If you watched the last episode, you'll know this, but I like to sort of catch you up to season 2. All right, here we go. So we talked about numbers, the number system, rational and irrational numbers. We're going to get into that. And we're going to tie it to how machines speak to each other because they're really good at talking with each other with numbers. They don't use this phrase rational or irrational. They're actually much more rational than us human beings. So there you go. They don't like wasting time on this terminology. Okay. Second thing is expressions and equations, functions. I'm going to do something to try to help you understand what that is if you've had problems understanding it. I know I did. Like as a kid, and even still, I'm dyslexic, so I can't put things together correctly. Sometimes, well, I say correctly, I mean it's my own way, it's your own way. It's a whole new world. You can be your way, I can be my way, right? It's totally okay. But I'm going to walk you through how I understand functions. And we won't get to geometry or statistics. Let's save that for episode 3 of the Sometime Sunday. If in a future Sunday I feel that I can do this again, we'll do that. Okay, so again, number system and functions. Ready? Okay. All right, but first, let's. I wanted to show you some stuff. You know, I have a show on LinkedIn called the 8 a.m.ish Get Physical show, where I walk through 5 objects and I think and learn through objects. Museum educators talk about this as object-based learning. So it's a different kind of learning. And math doesn't involve a lot of objects. It gets more expensive when you have a lot of objects too. So that's why it doesn't happen in schools, I think. But I'm an object thinker. So let me show you a few objects to sort of stimulate you as we enter the math world. I have some very fancy things for you. Okay. So first of all, you can hear the crinkle crinkle of plastic. That means important, archived. So this is, I don't hear I don't have the comments or whatever, so I can't see if anyone can see anything or I'm not sure. This is a real copy of Carl Gerstner's designing programs, and it's even inscribed by him. And it is a book by someone who, the letter. It is a book by Carl Gerstner, who passed away in the last decade. And he really kind of showed a linkage between math and art and design, like many artists and designers attempted to do in different ways. But I think that, the human figure was perceived as not mathematical and therefore more human. But I think a lot of interesting artists and designers were at that kind of border between math and art. And it was something kind of special, and they were kind of weird. So, and maybe weird people like each other, other weird people, but I just loved his stuff. It really it spoke to me because I didn't understand art per se, but I understood his art, and that became a gateway to understanding it. Segue to, I found in one of Carl Gerstner's book from the 60s, this man named Mitsuo Katsui. I'm tearing up a little bit. He was my mentor in Japan, and he would always send me stuff. He died recently, actually. That's kind of sad, but Katsui Sensei, we called him. He was like this amazing designer who was like designery, like non-math at all, but he could speak geometry and humanity in this very soft, wonderful way. And anyways, this is still on my wall, my kind of piece of the great Mitsuo Katsui. What a great man. He's a good, kind man. Okay. So anyways, Carl Gerstner, Mitsuo Katsui. And then let's bring a little bit of Ray and Charles Eames. Whoa, dropped it. 1 second. What did I do? Let me see here. Check. Whoa, I did something dangerous. Oh, well, that means I shouldn't touch anything. I deleted a scene, but you can see, so that's good. Don't touch video, John. Okay, this is called Cosmic View, which is AKA the Eames famous film, The Powers of 10. Everyone know Powers of 10? Maybe not. Used to be shown in schools back when there was no YouTube content. There were very few things like films and stuff there weren't many movies you'd watch in math, right? There was no animation, but there was this one thing called Powers of 10 that they would actually show you in math or science, and it was like kind of cooler than usual. And so Cosmic View is a book. It's about sort of jumps in space that start with a city map and a hand, and it's zooming out at a person, and it's zooming out. Okay, so if you watch Powers of 10, the movie, this is on a square. It's a little bit eerie. It's like basically If you ever seen the movie Powers of 10, it's eerily like this book here. You know, zooming out, zooming out, zooming out. Powers of 10. See that? It's all done with illustrations. Going into outer space, going into the galaxy, heading out to the universe, etc. And then zooming back down, and then getting into like the skin layer and the nervous system, etc. And getting down to atoms, etc. Anyways, this was the inspiration for the Powers of 10. If you see the Powers of 10 film, and you're like, wow, you gotta take heed to this work. Was the beginning of it. Again, not math, not art, not science. It was all combined together a long time ago, but I think the academic world kind of like broke them all apart, perfected them. It's not a bad thing, but we need to bring them together, right? Because that's how we collaborate. Okay. Oh my gosh, I'm sorry. I brought all my stuff. One more thing. I'll never get to the math before I get to the end of this lesson. It isn't really a lesson. It's sort of hanging out, right? So this is actually very precious. So this is an original copy of the book Flatland. I know. This is like, I'm not sure if I should open it. Well, anyways, there we go. It's an original copy of Flatland, which if you're a math sort of literary, like liberal artsy type person, it's kind of a magical original copy. It says price 7 shillings and 6 pence. I don't know what that amounted to when this was made in the whatever last century. Okay, so let's actually get to the heart of it all, shall we? So I want to talk about two things today. Numbers and functions. You ready? Okay, let's do this like in 5 minutes so you can go back to your life, and I have to finish my work. I have all kind of work, so, and you do too, I know. So we're on the same page, right? Okay, so let's make sure my audio is working. It's looking good. Go. All right, so number one, we want to tackle numbers, and we want to address this problem of irrational versus rational. Right? Because we hear we heard this when we were kids, and I don't think we ever used it. I stopped using it. We don't use it a lot. We use like dollars and cents. Like, you know, I'd like to buy that for $1, $1. And it's like, oh, you want to throw in some pennies there. So you want me to buy it for $1.20. And like, oh, well, you don't want me to buy it for $1.20. You want to buy it for $1.21, right? Okay. Now, in our world, we cannot chop the penny any thinner, right? But in the math world, you can chop that penny as much as you want. You can chop the penny. You can say like, I'd like you to pay me $1.21 and 1/10 of a penny. And can you actually make that 1/1500th of an extra penny, et cetera, et cetera, et cetera. So rational numbers, I think there's probably some great Wikipedia entry that explains it, but it's like, this is like a good number. It's not chopped up. It's easy. There's like complex stuff to add at the end of it. Irrational, that piece is adding all this funky stuff here after the number, which is really subdividing and subdividing and subdividing. It's kind of like, you know, this Eames power of 10 thing, right? Or like, actually, let's call it by the right thing. Let's call it the Kiesbach. I should learn how to pronounce this name. Kiesbach way of subdividing space. So like if you see here, he's got like a view of a woman over here in the park. And then that's a whole number. This is a whole number. And then we're going to like go like 10 to the minus 1, like insect, 10 to the minus 2, skin layer, 10 to the minus 3, et cetera, et cetera, et cetera. So we're getting like, we're subdividing space. We're subdividing the number. And math people love to subdivide things, like take something smaller, 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 smaller. It's like magic. And math's a lot about magic. And so it's kind of magical to think of taking a penny and then subdividing it to like 6, 2, 3, 4, 5, 1, 2. Can you imagine doing this all day long? And you're like, whoa, I subdivided that number. That's irrational. How did you do that? I did that with math. Maybe that's how it came out. I don't know. But rational and irrational numbers. Now in the computer, how do we reconcile this? Now that's the cool part. In computers, I mean, inside the computer, no one wastes time about rational and irrational numbers. We talk about two kinds of numbers. One number is called an integer. An integer is a whole number. It's a real number. It's a number that you can like not slice into things. It used to be bound to the kind of underlying bit structure inside the computer. Now there's lots of bits in the computer, so you don't have to like, you don't have to, what do you call it? Be stingy with your bits anymore, but we used to be really stingy with our bits. It was like you didn't have a lot of bits to mess with. So integers were the only way you could compute things. And you never had like sub pieces of numbers. You were never able to go like point blah, 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 blah. So-called floating point representation. You weren't able to do that. It was just too expensive. Expensive meaning expensive to have the hardware and also expensive to process it. But today we have a simple distinction. Integer types, and floating number types. So if you ever look at code, computer code, and you're like, well, why is this called a float or a double? Float and double. Like a double is like a deluxe float number, but floats and doubles are numbers that have all this subdivision. Whereas an integer, or also called a byte, doesn't have all this like fancy subdivision. You get what you pay for. You only get whole numbers. So integers are whole numbers. Floats and doubles have this fractional piece attached to them. Now, because you probably came here to learn how to speak more machine, we're speaking a little machine here. Got that? Integer and floats. Let's do it even one more level deeper with my money here. I have all these like coins from when there were all kinds of currencies, and I don't know what to do with them. I think I'll lose a lot of money in the exchange, but they're worth nothing, so problem. Okay. All right, we're almost done with this lesson. You can go back to your work. Me too. We have to do stuff to do. Not work, play, Sunday. Have a good day. Okay, so we got money over here, right? Okay, we have money. I think I pulled 8 coins. By the way, this is my mother's turtle ring. She likes turtles and frogs for some reason. We aren't sure why, but we love her for that. Okay, so we have 4 coins, 8 coins. All right. So it's hard to tell which is heads or tails. So I got my little stickers here. What can you see easier? You can probably see yellow easier, maybe. Green, maybe? Green's good, green. All right, so I'm going to put a green dot on one side of the money, which will mean like heads versus tails, basically. You know, it's 2 states, head or tail. Tails. Okay, so let's imagine you have a computer from a long time ago. It had 8 bits in it, and 8 bits means 8 bits means 8 states of 0 and 1. And so here it is. So let's call this, let's read this here. Let's say that if this is green, it's on. So that means on. Let's say that, let's define that as 1 means on, and then 0 means off. And let's take green and make it mean on. We're good? We're good, all right? Are they following me here? So we have like on, off, 1, 0. So with my coins here, if you see here, I've got 1, 1, 1, 1, 1, 1, 1, 1. That's 8 bits all turned on. And if I have them all turned off, I'm going to flip them upside down. And I've got 0, 0, 0, 0, 0, 0, 0, right? So, okay, did we get anywhere with that? We kind of did, right? Because you saw that I turned them all on, and then I turned them all off. Now, what happens if I turn just one on? Let me turn this one on. Whoop. So now it's 0, 0, 0, 0, 0, 0, 0, 1. 1. That's a good number, right? That's 1. So this is equivalent to 1, the number 1, expressed as 8 bits, and it is specifically an integer. There's no floating point number magic here. There's no like 1.123 whatever. This is like a raw 1. That's all you get. Okay, so that was pretty good. Okay, we represented the number 1. How do we represent the number 0? Oh, well, we just turned this off, and it's like 0, 0, 0, 0, 0, 0, 0. Oh, that wasn't bad, was it? Okay. All right, now I taught you how to count, and it's from 0 to 1 in 8 bits. Let's say I wanted you to count to 2. That's a little bit harder because you have to do something where you represent these different bits as different powers of 2. I know, powers of 2. Like powers of 2 mean like 2 times 2. Like 3 times 3. Like 3 to the second power is 3 times 3. So powers of 2. So let's sort of like start where this is called the least significant bit. Sorry, you're not significant. LSB. And this is called the most significant bit. Don't get too cocky over here. That's like you're the most important one. So the most significant bit is the highest power, and the least significant bit is the lowest power. Okay. Now, so this is going to be 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4, 2 to the 5, 2 to the 6, 2 to the 7. Okay. So what does that mean? So 2 to the 0 is 1. 2 to the 2 is 2. 2 to the 2 is 4. 2 to the 3rd is 8. 8 to the 2 to the 4th is 16. This one is going to be 32. I'm kind of cheating right now because I'm just multiplying by 2. That's easier because I can't remember how to multiply them all together. 64. 128. All right. Okay. So 1, 2, 4, 8, 16, 32, 64, 128. So if I want to represent the number 1, I flip this on. Boom. I have 1. And I want to represent the number 2, I flip this one on. That's 2. Boom. If I want to represent the number 16, I flip this on. Wow. That is 16. Hear that? See that? Kind of like Wheel of Fortune magic. And then I want to represent the number 128. I turn that on. Woo, 128. But that's not the biggest number I can represent because I can still flip these around. Right? So if I want to represent 129, I just take the 128 and I flip on the 1. Voila. You know, I'm now 128 plus 1 is 129. If I flip on this one over here, I'm now 128 plus 4 plus 1, which is, I know, you're thinking 133. I know, you're faster than me. So, again, all right, good for you. Well done. Okay, oh, that's beautiful. What is this? This Canadian coin is so nice. Look at that. It's got this kind of flower in the middle. But anyways, okay, so what do we have here? So what happened if we flipped all of these on all at once? What number would we get? We get the most interesting number that you've already heard. 255. Those of you who are in the computer world all know this number, 256, 256, or 255. 255 is significant because you're counting from 0. When you count from 0 to 255, that's 256 states. So you can represent 256 different states from 0 to 255 with just 8 bits as a integer number. We didn't get into floating point, but if you noticed, I only get to represent 256 different states here. That's 0 to 255 with 8 bits. That doesn't help me like go into an accounting program and say like that'll be $10.12. Where did I get the .12? Or like that'll cost you $2.25. Where did the 25.25 go? You can't represent it in integers, right? That's where floating point number magic comes, and that is beautiful. That is so hard to understand, but amazing. And floating point math, delicious. We'll maybe get into that, okay? If we can get out of episode 2. Phew, we covered a lot. All right. Oh, wait. I promised one more thing. Okay. We talked about rational and irrational numbers, or in machine speak, integers and floating point numbers. We learned integers really well because integers were how the world started. You're good there? But floating point numbers, a whole different ball game. We might touch upon that just to sort of like get real about it. There's a bird out my window. Hope you can hear the bird. It's real. This is on Earth, folks. Okay. So now we're going to talk about functions before we go. Because functions are how computer programs are comprised. If you remember episode 1, I wrote f of x. Like, what does this mean? F of x. I remember when I saw this, I didn't know what it meant. And maybe for like a year, I didn't understand what the teacher was saying. Because what is f? What is x? And that's because it's an abstract thought. And a lot about computer science is about what's called abstraction. It's about the ability to hold an idea inside a symbol or in a relationship of symbols. And it's not, I'd say it's not natural. It really is kind of this like higher primate function thing. So sort of finding your way into it is important. If you're like born math, or if your parents are like mathematicians or something, they could have taught you this when you were like a baby or something. But I didn't have any like reference for like, what is this stuff? So I accidentally found this thing one year in my life where I saw a picture of abstraction where it went kind of like, it was like an early animation of a box. Oops, excuse me. Like animation of a box. And the box has like a number coming into it. 6. And the number kind of like animates, and kind of like disappears in the box. Like, where'd the number go? And it's kind of like, whoa, where'd it go? Where'd it go? And it's because the number was an input. And once it goes in that box, you don't get to see it anymore. The only thing you get to see is the fact that the number went into the box. And then you wait, and you wait, and you wait, and then boom, out pops another number. It's like, I'm 7 now. Like, whoa, you were 6 over here. How'd you become 7, right? That's like weird. And so the point of a function is creating this kind of mystery of like, what is this box over here? Let's make it more like a box. Pretty much. What is this box where I put something in and something pops out like that? What is that box? Now, this is where that metaphor, the black box, gets used, which makes it even harder because there is no black box, when people talk about this. So it's a box. It's called a black box. Make it black. In comes your number. Out comes something. Think of this as kind of exciting. Like, well, what's in that box? How did that box turn 6 into 7? Like, what did it do? That's what an equation does. And when you think about this box, just refer to it as your friend f of. It's like f of, my friend f of. It's like, I got a box. And it's an f. It could mean all kind of things, but like f of, right? It's like an f of box. And then when I pop in this number here, it can be anything. Let's say my next number I drop in is going to be 3. And then out pops 4. And you're like, my friend f of this box. It's a black box. They call it a black box. Sometimes it's black, sometimes it's not. It isn't even a box. Number comes in, something comes out. Whoa. This f box. F of 3 is 4. F of 6 is 7. I wonder what f is. Like, what's in f, the box f? Well, that's the magic of math, because mathematicians can just be fine there. They don't have to understand what's inside f. They can like go off and have a coffee. By the way, I have a coffee here, just sort of like stay awake late tonight. A coffee. So f of, that was good. Uh, so f of 6 is 7, f of 3 is 4. I'm going to have my coffee, go to sleep. I've got this magical box f. I'm good. I want to use that f, and I'll use it in all kind of ways. So this ability to be abstract in how you think, be okay with not having to know what's inside, that's what a lot of great mathematicians can do. They can take this complex thing and like mush it into like either a variable or an equation, and they're okay with it. And previously, before computers, before computation, before writing code, only mathematicians could speak in their secret language of mathematicians. But because of computer code, it's possible for people who make things with their hands to actually construct these boxes, construct these relationships, build what's inside these boxes. It just requires understanding this language of integers, floats, procedures, f of, being able to call this, instead of 3 or 6, call it x. And then for this thing that pops out, call it anything you like. But to accept abstraction is a way to work with these essentially streams of numbers that flow through the box. And secondly, to be able to craft what's inside these boxes with either computer code or, increasingly now, machine learning algorithms. Well, people don't call them algorithms anymore. Machine learning systems that basically there's no code to write. So that whole new world is happening. It's about making these boxes do things with numbers that go in them and numbers that go out of them. And that's what functions do. Okay, we got through a variety of things. I think that my YouTube worked. Thanks for tuning in to episode 2. And maybe in a future Sunday sometime soon, I will continue this 8th grade interpretation of math. Are you with me? Okay. And, my gosh. And I will see you sometime soon, yeah? Okay. All right. Good seeing you, and have a great day.